Rational expressions add and subtract. You might be surprised to figure out that addition and subtraction is a little bit more complicated than multiplication and division. With multiplication and division, you just had to factor and reduce. Division required also keep, change, flip, but that was pretty much it to it. Adding and subtracting is a little bit more strict. You have to have a common denominator. If you don't have a common denominator, then you need to invest in figuring out what that is first before you can perform the operations. Once you do have a common denominator, the rest of it really isn't too bad, except that you still got to look to see if it simplifies at the end. Okay, so overall though, addition, subtraction, it is going to be a little bit more complicated than multiplying and dividing. All right, to start things off, example 1, we're going to add and we're going to subtract two rational expressions, but they already have common denominators, which means you don't need to figure those out. Okay, so once you do have common denominators, or if a problem starts with them, all you really need to do is perform the operation with the numerator. So for the first, all you got to do is take 7 plus 3. You already have the common denominator, 4x. So you're going to keep that denominator, and the top is going to become 10, which does reduce. So you don't see this until after you do the adding or subtracting, but it does reduce by a factor of 2, which will be 5 over 2x. All right, so for subtraction, again, you've already got a common denominator. Here's the catch to the subtraction though. If you have a binomial or a trinomial, something that has multiple terms, you have to make sure that the subtraction gets distributed to both of them. Okay, again, the very first term, you're going to get that right. It's going to be the second term that you got to pay attention to. Okay, so we are going to get 2x minus x which of course is just going to become x. But you also have a minus 5. Okay, so then it all cleaned up is going to be x minus 5 over x plus 6. That distribution is the most important part of this problem. Suppose that we don't have a common denominator, such as this case here. If you don't have a common denominator, what you want to do is factor your denominators to see what they're built out of. All right, so the first, you've got 9x squared. That is built out of a couple of 3's and a couple of x's. But we're going to hold off on that one until we look and see what the other one does. Okay, so our other denominator, this would be Gcf factoring. You can factor out a 3x, which is going to leave you with x plus 1. Okay, now seeing that in factored form is going to tell us what we might want to do with this monomial. Okay, I can actually split that into 3x times 3x. And now that I have this factored out, what I want to do is figure out what makes each one of them unique. They both have a 3x. That's in common. What is unique? This has an x plus 1. And over here, we have a second 3x. That is a unique thing to that denominator. And whatever is unique, you're going to want to share it to the other fraction. And that's what's going to create your least common denominator. All right, so let me reset the problem over here. We're going to have 7. We're going to break that up into 3x, 3x. Then we've got plus x over 3x times x plus 1. So same thing that we already had. But now what we're going to do is share those factors. Over here, we've got that x plus 1, okay? So we're going to share that to the other side. You're going to multiply the top and the bottom by that factor. And the second fraction needs to get that second 3x that we had there, okay? So top and bottom. As far as the bottom is concerned, just leave it in factored form. Okay, we could do 3x, 3x, x plus 1. Don't actually multiply things here, because if the top creates any factors that would match to the bottom, then you're able to reduce a little bit later on. Okay, now for the top, we're going to need to multiply and see what we get. So we're going to get a 7x plus 7. Over here, you're going to get 3x squared. Okay, so what we end up with here is a quadratic polynomial that is not in standard form. Let's go ahead and fix that up. All right, now we'll have one more task to do. We're going to consider whether or not the top can factor. Okay, there's no guarantee that it does factor, but if it could, this is what we would do. We would use factoring by parts. We would think about 3 times 7, which would be 21. And we would ask ourselves, can we think of two values that multiply to give us 21 and add to give us 7? And the answer to that would be no, because the only factors that you could be using would be 3 and 7, which add to give you 10, or 1 and 21, which would add up to give you 22. Okay, so the top doesn't factor, which means it's not going to reduce with anything that's in the denominator. Okay, so we can actually leave our answer here, except what I want to do, just because it's easy enough, is go ahead and call that 9x squared. All right, I'm going to make a note here that our answer that we have is a little bit weird because the numerator is in standard form and the denominator is in factored form. You do have the option to distribute this in and change into standard form, which in this case really wouldn't be that much work. However, in some other problems, you might have 3 factors in the denominator, which makes that process really long. So even though we have a conflict between the numerator and the denominator, we've got standard form and factored form, we're going to let this answer be. What we're really teaching here is an intermediate step to something that's going to be bigger in the future. Okay, so we're not going to make it harder than it needs to be right now. Example 3, we've got subtraction. And what I'm going to do from the very beginning is I'm going to distribute that subtraction into the numerator that follows it. Okay, so if I distribute that in, I'm going to get a positive 2x and a positive 1, which, by the way, none of that factors, so I can just write it now. I've got 2x plus 1. In fact, I'll just put a plus there too. This also doesn't factor, okay? Kind of just as it is for right now. The bottom, actually, let me take that out because it might be distracting. Okay, now for the bottom, we're going to factor because obviously these are not common denominators. Here, we've got a GCF. We can take out a 2. Over here, what multiplies to give us 3, but adds to give us negative 4. Those will actually both be negative numbers, which will be x minus 3, x minus 1. Product is positive 3, but the sum of them is negative 4. Okay, so what is unique here? They both have an x minus 1, but this has a 2, and that has an x minus 3. Okay, so resetting the problem, we've got x plus 2, it's taken from here. The bottom is going to have a 2, x minus 1. And we're already going to change this to addition because I already distributed that in. Okay, the new factors that this is going to gain are going to be x minus 3, top and bottom. Okay, so the second fraction, 2x plus 1, you've got these already, but it is going to gain the 2. All right, so let's go ahead and multiply this to see what we get. We're going to get an x squared. You're also going to get a negative 3x and a positive 2x, which will give you negative x. We also get negative 6. Our factors, I'll reorganize them. Looks like that. Okay, and then the other fraction, we can just distribute the 2. Okay, so we're going to get 4x plus 2. That would also be over 2, x minus 3, x minus 1. Next, what we'll do is group all the like terms that we have in the top. Okay, let's go ahead and write down the denominator. In the top, we're going to get an x squared. We're going to get what would be 3x. You would also get a negative 4. And we're going to consider one more thing. can we factor the numerator? Can we think of two numbers that multiply to give us -4 and add to give us 3? And we can. Those numbers are going to be 4 and -1. Okay, so above this, I'll just write it. We got x plus 4. We have also got x minus 1. And in this case, since you can factor the numerator, we do, and then we compare it to the denominator and see if anything does match. There's a chance that nothing does. In this case, it does. Here are two factors that we could cancel out. Oh, I forgot that there. Two factors that we can cancel out. We end up with x plus 4 over 2 times x minus 3. For example 4, we got the old intimidating complex fraction. But don't really be that intimidated by it. All this ultimately turns into is one big division problem right there that you use keep, change, flip for. All right, but before we can do that, the bottom here, we're going to need to add those together as a single fraction. Once we have them as a single fraction, we can do some keep, change, flip with the overall thing. Okay, so let's work off to the side here. We've got 1 over x plus 4 plus 2 over x. Okay, these denominators are relatively prime to each other, even though they both have an x in them. This is an x plus 4, which you have to treat as a combined item. It's a binomial, and that's different than x. Okay, so these are relatively prime. They don't actually share any factors. What you'll do is just multiply the top and the bottom of each fraction by the other one's denominator. That would be an x here and here, and this would be x plus 4, x plus 4. All right, so the top is going to become x plus 2x plus 8. Okay, x plus 2x plus 8. So that's going to give us 3x plus 8. The denominator, we'll leave that factored. That's going to be x times x plus 4. Okay, so this represents that denominator. So now that we know that, we can do keep, change, flip. We're going to take the 5 over x plus 4, and we're going to multiply it by the reciprocal of the denominator, which is the reciprocal of this. Okay, so you got x plus 4 for the top, over 3x plus 8. And you're going to notice that we did end up with one common factor, which is here. So you can cancel those out, and you're left with 5x over 3x plus 8. And that's it.
Later, blah.